of October 2025, Unit 2. We move to Section B. We will be solving some selected questions. One question is this: another sample of impure calcium oxide made from heating limestone has a mass of 5.12 grams. Impurities do not react with hydrochloric acid. Okay. So you have impure calcium oxide that has a mass of 5.12. This is the mass of calcium oxide along with impurities. It says the sample is added to 200 cm cube of 1 mole per dm cube hydrochloric acid. Forming a solution, the hydrochloric acid is in excess. The solution containing excess acid is transferred to a volumetric flask. Okay, it's transferred to a volumetric flask and it is made up to a volume of 250 cubic centimeters using deionized water and then mixed. A 25 cm cube sample of this diluted solution is titrated with 0.15 moles per dm cube sodium hydroxide. The mean titer is found to be 23.7. Okay, so calcium oxide was reacted with hydrochloric acid. This hydrochloric acid was in excess. And after the reaction, the remaining HCl was dissolved in water and made up to a solution of 250 cm cube. And out of 250 cm cube, 25 cm cube was taken out. From 250 cm cube, 25 cm cube solution was taken out. Okay, I repeat, from out of 250 cm cube, 25 cm cube of the solution was taken out. And a sample of the solution, 25 cm cube sample of the solution was then titrated with sodium hydroxide. So the remaining HCl, the HCl that did not react with calcium oxide, was dissolved. Was made up to a solution up to 250 in a volumetric flask, and out of which only 25 cm cube was taken out and titrated with sodium hydroxide. So initially what we do is we find the moles of sodium hydroxide. So sodium hydroxide, we have concentration, we have volume, you multiply concentration 0.15 multiplied by 23.70 into 10 to the power minus 3. This is the moles of sodium hydroxide. If you calculate, this would be 0.15 times 23.7 divided by 1000. This would be equal to 0.003555. This is equal to, which is equals to the moles of HCl in 25 cm cube, because you titrated 25 cm cube of HCl. Then we find the moles of HCl in 250 cm cube. In 250 cm cube, the moles of HCl will be 10 times more. 0.003555 times 10. This would be equals to 0.03555. Right? So if you multiply by 10, this becomes 0.03555. In 25 cm cube, that's the number of moles. In 250 cm cube, the moles will be 10 times greater. Just use simple unitary method. If 25 cm cube has this mole, 250 cm cube will have 10 times more the moles. Then what we do is, so this is basically what? This is basically the moles of HCl that remained, right? That is unreacted. This is the moles of HCl that was unreacted. Right? This is the moles that didn't react. Then we calculate the moles of hydrochloric acid added, or the initial mole or the added moles. The moles of hydrochloric acid added was 200 cm cube. The volume was 200 cm cube. Concentration was 1. So this would be equals to 1 into 200 into 10 to the power minus 3. So this would be 0.2 moles. Right? 200 divided by 1000 is 0.2 moles. Then you calculate the moles of HCl that actually reacted. This would be equals to added minus the unreacted. So the added mole is 0.2, unreacted is 0.03555. So minus 0.03555 will give you 0.16445, right? That's the moles of HCl that actually reacted. Then we find the moles of calcium oxide reacted. Moles of calcium oxide reacted will be, because the mole ratio is 2:1, so moles of calcium oxide reacted would be half multiplied by 0.16445. So this would be divided by 2. This would be equal to 0.082225. That's the moles of calcium oxide reacted. Then we find the mass of calcium oxide. The mass of calcium oxide would be 0.082225 multiplied by the molar mass of calcium oxide. If you look at the molar mass of calcium oxide, we have to find the molar mass. Calcium is 40.1, oxygen is 16. So the molar mass of calcium oxide is 40.1 plus 16 is 56.1. So if you multiply, your answer comes out to be 4.6128 grams, right? Then you find the percentage. You are asked to find the percentage purity, right? So percentage purity will be equals to 4.6128 divided by the total mass of calcium oxide along with impurities. So divided by the total mass was 5.12 multiplied by 100. This gives you 90.1%. Right? So this is how you solve this question, and I think we got a similar question in the previous year. So back to back 2 sessions, they gave a similar question. So you should consider this question as a very important question. All right. Okay. Now we move on to question number 20. It says, why chemists often use reaction number 2, formation of a nitrile, when synthesizing organic compounds. Now reaction number 2 is the reaction with potassium cyanide. You are reacting the halogen alkane with potassium cyanide producing a nitrile, because this is the only reaction that we have ever studied which can increase the number of carbon atoms in an organic compound. If you look at this compound, in this compound we have 3 carbon atoms, 1, 2, 3. We have 3 carbon atoms here, 1, 2, 3. But if you look at this compound here, we have 1, 2, 3, 4 carbon atoms, 1, 2, 3, 4, right? So this is the reason why chemists often use reaction number 2 to increase. Your answer would be to increase the number of carbon atoms in the carbon chain. All right. Then we move on to question number D. It says, why anhydrous calcium chloride is added to ethanol before it is used to dissolve sodium hydroxide? It says a different type of reaction occurs when the halogen alkane, this chloroalkane is heated with sodium hydroxide dissolved in ethanol. So you get elimination. It becomes elimination. You get an alkene. 1-chloro-2-methyl cyclohexane is heated with sodium hydroxide dissolved in ethanol. So this will cause elimination reaction. Why anhydrous calcium chloride is added to ethanol before it is used? Before you are using ethanol, before you are using before you're using ethanol to dissolve sodium hydroxide, right? So why is ethanol being treated with anhydrous calcium chloride? Because anhydrous calcium chloride is a drying agent, so it will remove water. So the main role of anhydrous calcium chloride is to remove water from ethanol. Now what happens if you don't remove water from ethanol? See, if you don't remove water from ethanol, what happens is that otherwise water in ethanol would substitute the chlorine, producing an alcohol. See, in this reaction, we are not here to produce an alcohol. This reaction should produce an alkene because it's an elimination reaction. If you react with sodium hydroxide dissolved in ethanol, this reaction results in an elimination reaction. Elimination reaction will always produce what? Elimination reaction will always produce alkenes. We want to produce an alkene here. We don't want to produce an alcohol. Now, if you forget to dry the alcohol, if you forget to dry the ethanol, now what is going to happen? If you forget to dry the alcohol or the ethanol, now what's going to happen here? The ethanol, since it contains water, the water in ethanol will basically, what it would do is, it would substitute the chlorine in the halogen alkane. It will substitute the halogen, producing an alcohol. We don't want to produce an alcohol. This was a very good question, a very different question. It says, draw the skeletal formula of the three isomers formed in this reaction. You have to draw the skeletal formula of the three isomers. If you want to draw the skeletal formula of the three isomers, let me draw the skeletal formula of this one first. Just a minute. So this is the hexagonal ring structure. Then we have chlorine here, and a methyl group and an ethyl group here. Okay, and there's chlorine here. That's the structure, right? So we'll eliminate H and Cl. Let's look here. So what you have a hydrogen here. You have a hydrogen here. When hydrogen and the Cl gets eliminated, if you eliminate them, so you'll get a double bond here. So this is one of the answers. You get a double bond here, okay? Then there's also hydrogen here. There's a hydrogen here as well. There's a hydrogen here. Now if you eliminate them, because there's another hydrogen here, if you simply eliminate them, so you get a double bond here. Right? You get a double bond here. Now this alkene has a geometric isomer. So in order to show the geometric isomer, what you do is you interchange these two groups. Right? What we do here, we change the groups here. We put the larger group above the double bond and the smaller group below the double bond. Right? We have changed we have actually changed the two groups here. We have put this group was above the double bond. Now this is below the double bond. This ethyl group was below the double bond. Now it is above the double bond. So these are the three skeletal formulas that you can draw. All right. Now we move on to question number. Next question, which is question number 23, I think. Okay, 23, B1, nor B. It says the reaction mixture is placed in a pear-shaped flask and heated for 30 minutes. Name of the additional piece of equipment when heating the reaction mixture for this length of time without any loss of the mixture. It should be a reflux condenser, right? If you heat for a long time and if you are dealing with volatile liquids, you must use a reflux condenser. It says describe the color change that occurs during this heating. The color change that occurs during each heating is orange to green. Because you are reacting with potassium dichromate. Potassium dichromate is orange in color. And during the reaction, being an oxidizing agent, potassium dichromate will get reduced to chromium 3. So there will be a color change from orange to green. It says how the infrared spectrum of the reaction mixture would change during this reaction. You should consider only the organic reactant and product. Use information from the data booklet to support your answer. You have to consider only the organic reactant and the product. Okay. It says it's used to oxidize propanol in a laboratory. So you are oxidizing propanol. Let us draw the structure of propanol. Basically, in order to answer this kind of questions, you should draw the structure, it's best to draw displaced formula. So, or you can also draw structural formula. For example, I'm drawing structural formula. Not actually structural formula, it's a mix of both structural and displaced formula. This is propan, my bad, I made a mistake. Now that's propan 2-ol. Now if you oxidize propan 2-ol, it produces propanone. Now look at the changes here. Look at the bonds here that changed. There were 3 bonds that actually got changed. One bond is that the OH bond is not there. So the absorption for OH, the infrared absorption for OH would disappear, right? There is another bond that also disappeared, which is the C single bond O. So the C single bond O and the OH bonds, the absorption for these two would disappear. And there's a new bond that is formed here, that is C double bond O. So the infrared absorption for this bond would appear. These are the 3 things that we should write. Usually this question is of 2 marks. Now this is of 3 marks. That is why we are here we have to write 3 points. So 1 point will be about the disappearance of the OH absorption and the disappearance of the CO absorption and the appearance of the C double bond O absorption, right? So what would we write here? We will write IR absorption at 3750 to 3200. Now this range is copied from the data booklet. For OH would disappear, right? And we write the same for the C single bond O, IR absorption for the C single bond O from the data booklet. For the C single bond O from the data booklet is, you have to, let me bring out the data booklet. I don't have this data with me right now. I forgot this data actually. Data booklet. Just a minute. Data booklet, C single bond O. Oh, the data booklet doesn't have any absorptions for C single bond O. So you don't need to write the wave number here. You can just simply write the infrared absorption for C double bond O would disappear. That's it. You just write this. Okay. And then you have to talk about the appearance of the CO bond. So we write infrared absorption at for C double bond O, since it's a ketone. According to the data booklet, it is 1720 to 1700. At 1720 to 1700 per centimeter for C double bond O would appear. This is how you write the answer. All right. Okay, then we move on to the next question. It says you have to calculate the mass of benzene in kg needed to produce 2000 dm cube of propanol using this particular process. Now, whenever you are asked to find the mass of the reactant, you must find the theoretical yield first. In order to find the theoretical yield first, we should find the mass of the product. Now, the mass of the product, which is the product here? Propanone. Propanone is the product here. So you have to find the mass of propanone. How do we find the mass of propanone? Mass of propanone will be density multiplied by volume. What is density? 0.784 multiplied by volume. The volume was 2000 dm cube of propanone. So you have to multiply it by 2000. Now you can't multiply by 2000 because it's in cubic centimeters, the density, and the volume is in cubic decimeters. You have to convert the cubic centimeter convert the cubic decimeter into cubic centimeters. So you have to multiply by 1000. So if you multiply by 1000, your answer comes out to be 1.568 into 10 to the power 6. So this is the mass of propanol that is required, right? Then you need to find the theoretical yield of propanol. In order to find the mass of the reactant, you must always use the theoretical yield. How do you find the theoretical yield? Now, this is the actual yield, 1.68 into 10 to the power 6 grams. This is the actual yield, right? From this, we want to find the theoretical yield because the yield is only 85%. So you divide by 0.85. If you divide by 0.85, so your answer 1.568 into 10 to the power 6 divided by 0.85 will give you, let me calculate, 1.568 into 10 to the power 6 divided by 0.85. This gives you 1.844706 into 10 to the power 6. Okay. Then we find grams. Then we find the moles of propanol from the theoretical yield. So this would be 1 point this divided by the molar mass of propanol. Now the molar mass of propanol is 12 plus 16 plus 30. 12 plus 16 plus 30 is 58. So divide by 58. So this divided by 58 gives you 31805 moles. Okay. So which is equals to the moles of benzene, because all of these substances, propanol, C9H12, all of these, they have the same mole ratio. The mole ratio is 1:1. They all have all of the substances have the mole ratio 1:1, right? So that is why the moles of benzene would also be the same. Then you find the mass of benzene. Mass of benzene will be equals to 31805 multiplied by the molar mass. 31805 multiplied by the molar mass of benzene is 78. If you multiply by 78, 31805 multiplied by 78 gives you 2480800 grams, which is equal to, you're supposed to give the answer in kg, right? So you divide by 1000. This becomes 2481 kg, right? So that would be your answer. Easy question, very, very common question. Then we move on to question number D. It says compare and contrast these physical properties. Justify your answer in terms of intermolecular forces. Okay. So you have to compare and contrast, means you have to talk about similarities and differences about these physical properties. Now, both of them are soluble in water, right? Both propan-2-ol and propanol are soluble in water because they both can form hydrogen bonds with water. Both propan-2-ol and propanol can form hydrogen bonds with water because they have OH, because propan-2-ol has OH in it and propanol has oxygen in it, which allows these molecules to form hydrogen bonds with water, and that is why they are very much soluble in water. They are fully miscible in water. Now, propan-2-ol and propanol, they have very different boiling temperatures because propan-2-ol is able to form hydrogen bonds with each other, right? Whereas propanol is not able to form hydrogen bonds with each other. Propan-2-ol can form hydrogen bonds with each other. Propanol can't form hydrogen bonds with each other because propanol doesn't have OH in it, right? And that is why propanol has London forces and permanent dipole forces. Propan-2-ol has all of the forces, and that is why propan-2-ol has the higher boiling temperature, and hydrogen bonds are stronger than the other types of intermolecular forces, right? So one point that you can write here, that both the compounds are able to form hydrogen bonds with water. Both the compounds are able to form hydrogen bonds with water, right? Now propan-2-ol has hydrogen bonds, or propan-2-ol forms hydrogen bonds with other propan-2-ol molecules. Right? Propanon cannot form hydrogen bonds with other propanon molecules, but forms London forces and permanent dipole forces. And then you have to write hydrogen bonds are stronger than the other types of intermolecular forces, thus requires more energy. Yeah, that's how you write the answer. This is a very common question. This type of questions we always expect to get this type of questions in the exam. Yeah. All right. Okay. The end of this paper. Yeah. Thank you.